Yes, we can.
Yes.
Well, we will talk about that research project that started a few years ago to resolve some problem that we have in the Internet of Things devices and devices mainly. And we try to mix that kind of techniques like a polyform cipher and use another technique like one-time password to exchange the cryptography of the channel that exchange information between Internet of Things device. Well, this is the agenda. First ones, we talk a little bit about the motivation from that work, some concept that is important that introduce for understand our results, and the origin of our hypothesis that's going to resolve with this work. And the main focus will be in the detail of the algorithm and present some results, basic results, and the next step for the future works that we develop in that kind of project. Well, the main project basic, you know that the Internet of Things are increasing the use of that kind of devices to enhance the capacity of the operation technology in different kinds of enterprises. Then some critical information is passed about the channels between peers. For example, channels that origin data in embedded system and move to the MTU or vice versa. Yeah, that's the information. Let me check. I don't know what's happened with it. Well, then that's information could be intercepted for some kind of attacker. Then the problem that we see with the end device, that's the research available for that kind of embedded system is so short. In that case, we have a lack of memory and we have a lack of cycle of CPU. Then it's so easily to implement some kind of attack that could be alter the information that's shared between the peers. That is usually that some kind of hacker use man-in-the-middle attack to alter that information that could be critical for the operation technology. Then that is the main problem, but the second main problem is the devices that is used for the end points is devices that use a short of they use the resource very short in memory and CPU cycles. Then we try to resolve the problem to implement some CryptoBox to protect that channel, and CryptoBox that could be used a short cycle of CPU and a short space of memory that could be run inside of embedded system or a low-cost embedded system. That is the key of the main problem. Well, we observe in the nature that is so useful. It's so useful that some kind of insect like butterfly change his features using 2 or 3 characteristics. For example, in that image, we see that the butterfly change the shape of the flights, interchange different kind of color. For example, orange colors or brown color or different kind of pattern. And that is the concept of mutation that is very usual in the natural form. Then we ask that that kind of mutation is possible to apply to create a key that could have some kind of mutation to enhance the CryptoBox that we use to protect the channel. That is a concept that could be tried to apply to create the cipher box. Then is another concept important is that kind of technologies that Probably you can use the one-time password, for example, for what is two sequence of validation when you take some money from the bank, or you have some transfer information. That one-time password is usually used when interchange token that is generate a sequence that is synchronizing between the peers and protect the information, and the password is used one time. Then the password expires, but then for the another transaction you need to use another password. Then that's with two main concepts. We have it's possible to create some kind of mutation for the key that we can use to protect the channel of the device or the end device. And we create that hypothesis, but this is possible to use the polyformis one-time password technique for the mutation of the encryption key. This question that we can resolve with this work. And how much could be the computational cost of implement that kind of polyformic and one-time password technique? And the most important is that kind of algorithm is possible to implement in embedded system that is usually used for the endpoints and have a little bit of resource to implement not only the operation technology, instead implement more algorithms that to protect the channel. That is the idea. And I think that there's another question that we must to resolve is if our proposal could be used to protect channel that can use another kind of protocol that protect that channel. Then we, for answer that kind of question, we say that it's possible that we can, our model implement only in the payload. Then in that case, if you have different kind of protocol that is used for transport information in the channel, is irrelevant if you alter the cipher payload that is used to interchange messages between parts. That is the encryption scope that we use for the solution that we will propose. This is a basic encryption process. In that case, when you exchange information between the peers, you need a message. That the message could be in a flat text, or maybe could be a message that is with the basic crypto box that is implemented in the transport protocol. Then that's independent for our model. In that case, we take the message and we try to adjust the size of the message, because it's necessary that the message have a size that have a multiple of the size of the key that we select to make the encryption. That is the first key. And then we add some zero at the left for create a size of message that is a multiple of this selected key. Then the second step is to extract a part of the message that's not be a cipher in the first exchange of information. That's we talk about that kind of number in the next slide. That's with that number we use for select the different kinds of reversible function that is applied with the combination of the key to make the cipher of the message. In that case, we use a sequence of reversible function, and we take that reversible function and apply for a key, and that information is applied for the create the cipher message. Yeah, when we apply that function, we create a cipher message that is sent to the peers. In that case, that is the basic of our proposal, how to create that kind of exchange information in that process. For that, we propose to create a new header that is implement in the cipher message. The header have 3 fields. The first field is ID. That ID is important because in our purpose could be applied for different kind of topology. For example, it's possible, depend of the resource of the peer or the embedded system. In that case, we can implement topology like peer-to-peers or topology like full mesh topology. Then we use one ID for each peers with exchange message. That is so interesting because it's possible to create different kind of topology that could be implement Internet of Things exchange message. The second one is a type code that is used mainly to differentiate the kind of message, and we will talk about that in the next slide. But the PSIN, that is a polymorphic sequence nibble, is a number that we use with the size of the 4 bits size that we use to alter, to create some mutation of the sequence of reversible function that we use to make the encryption. That could be important because we select from the message that's number from the message, and the position of this information could be in any kind of part of the message that we need to cipher. That is very, very important for the algorithm. Well, that is the 4 type of fields that we use. The first field is the first contact message, the first code that is used because we need to, when we start communication between some peers, the IoT device that is used for start the communication create with that key some ID that is used for the different kind of table if you use a mesh topology. That is so very important. With that first contact message, you say, well, that is my first message that you send to that peers, and that message used for create the basic key for exchange and cipher the next message. The second type of code that we use is the regular message, but this is the normal message that we cipher when we start with the first key, the second, the third one, and so on, is used for ciphering and indicate to the peers that is the same regular message that we sent it and is ciphered with style. And another code that we use is the key update message that is used in case that some peers want to update the table key. For example, we construct in interchange in 2 keys in between 2 peers, we construct 2 tables, and that 2 tables could be updatable. For example, some peers say, well, that table is not used for me, and we send a key update message for in the next message, we try to construct another tables that is used for the posterior message. And the last type of field that we use is the last contact message that is used to release the memory with the peer-to-peer communication. In that case, that is the last message that I send you to the another peers. And in that, well, you could delete the key that you construct in the first message, and we can use the memory for another kind of task. That is the 4 fields that we use in the header. Well, the key of our proposal is to use 3 main functions. That's main function that could be pre-programmed in the embedded system. In that case, we pre-program that 3 functions in the peers that we use for embedded system. And these functions could be customizable. Yeah. Depend of the kind of function that we use, you can program that function, and that function that is common in the 2 peers for that protocol function, for that the cipher method function. That is the tricky. First one is the scramble function. The scramble function is to alter the basic numbers that's exchanged between the pairs. The second generation function is to create any kind of key, and the mutation function is to alter the original seed that is used to create any kind of key that is used in that protocol. That could be a little bit, it's complex, but it's so simple to implement. I will try to explain so well in the algorithm. That is a basic of the algorithm that we use. Well, we start with the first message that's exchanged between the pairs, and any pairs exchange numbers. For example, the pairs that start the message send to another pairs the numbers P and the seed S. And as the response, the second pairs return a Q number. Then both of pairs have three numbers: P, Q, that's some prime numbers, and a S, that is the C that could be used in the algorithm to calculate the key table. Then it's necessary that any pairs create some number n, that is the number of key that we can use for the exchange of different kind of message. Well, after we exchange that message, we start with the scramble function, and we use the number PR and the seed S to calculate the embryo key number. The embryo key number is a number that could be used, could be mutated in any calculation to calculate the key that is stored in the table that is used for the cipher system. In that step, we have with the scramble function calculate the embryo key, and with that embryo key and the Q, that is the another number that we use, we calculate the first key that we store in the table. That is a procedure that is executed in both pairs. In that step, we have one key calculation. Then second one, we create the mutation function. The mutation function uses the original C, S, and the second number, Q, to create a C mutation. In that case, S0. Then the seed that is used for calculate the first key is different to the seed that can use for the calculate the second key and the next key that we calculate with the algorithm. Then, in that case, we have one key, we have embryo key P0, and we have the C mutation S0. That I use the three numbers that's exchanged in the first contact message. Then we must prove that decrease the number of key that we need to create and pass to another step. We need to ask, is that the last key that we generate, but it's not the last key generate? Then we calculate the second embryo key. But that new embryo key is calculated with the basic Q number that exchange between the pairs and the C calculation for the mutation function. That's pass is in that case. Let me check. We calculate S0, and for that new embryo key, Q0, we use the Q original because we don't use to calculate the embryo key. Then in that case, that number is not used. Then in this moment, we have a new embryo key that is Q0. And with that embryo key, we calculate the second key that is stored in the table. In this kind, K2, we use the generation function with the Q0, the embryo key Q0, and the embryo key P0. That is calculated in the last step. Then, with that one, we calculate a new C mutation. That would be S1. S1 is calculated with the mutation function using the seed S0 and the embryo key P0. And that algorithm is repeat to reach the total of key that we need to cipher model. That is more complex when we start to the algorithm. I try to explain that procedure, but it's simple. We start with three numbers, basic three numbers, and the four number that is an index. These three numbers is used to calculate embryo key that use the first numbers and the seed, the first seed S. That's two numbers, calculate the embryo key, and we calculate the first key with the Q number and the embryo key P0, and then we mutate the seed key, the seed number, and we calculate with the mutation function the seed number S0 using the original seed number and the Q number, and so on. And with that case, we have a table that it's calculate any kind of key using a mutation. Yeah. In another kind of protocol, you use the prime number that's exchanged, so complex function to calculate all the keys that we can use for the cipher message, and another kind of technique. In that case, we mutate the key for the message that we can use. That is so very important because for each message that we exchange, we use one key, one pair of key. That's in the second message, we use the pair of key. The three message that we use or another pair of key, and so on, the system. Well, with that keys, we have a complete number of key in the dot in both IoT device. Well, in that case, we can pass to here. We have all information that is calculated in each pair. We have that key table. We have the pre-programmed reversible function. And with that two information, we can cipher the message. And any pairs of key is used with the index that we increase that index with the number of messages that you send. Well, with the key table generated in the system and the set of reversible function, we apply the algorithm, apply the process of cipher. In order to apply the reversible function, we use the PS number, and the polymorphic sequence number, nibble, of the last masses exchange. For example, the last message that we exchanged was the exchange of the numbers, and we use the PSN that is in the nibble last significantly nibble. The PSIN also serves as a pointer for the selection on the next PSIN. Then the first PSIN, we take that PSIN from the last significance nibble, and is used as pointer for the next PSIN. In that case, we select different kind of number of the message that we use to cipher the channel. That is so very important because in that case, that number select different kind of function that the reversible function that we apply to the cipher of message. That is very strong mechanism to cipher the message because for each message that we send, we use different key to make the cipher and use different reversible function that is to apply to the message. That is very strong. When we try to destroy the function using brute force tools, then it's possible that we can decrypt the channel, but the next message that is sent change the information that used for cipher the message. That is so strong to block. We use for the test bench, in that case, in simulation, we use the cube carbon tools for create different kind of topology. In that case, we use a topology peer-to-peers, and we use a topology with hardware for the low-end embedded system, that the ESP A266. That is a small chip that is used for Internet of Things. And with that information, we apply the algorithm to create the key and apply for test the strength of the CryptoBox. Then we evaluate the memory and the processor utilization, and we create some benchmark for the key loss rate that we can create for any message that's exchanged. I remember that the test bench use 1 million of messages that's exchanged between the peers in the two scenarios. Very important is is the result. In this one, the cryptographic box represents only 1% of the flash memory that is used compared with that used for the code for the process of operation technology. In that case, is very small the memory used for the tables. And the process of encryption and decryption times are completely asymmetric, but it uses that number of time to process or encrypt any message and decrypt the message. That is apparently a lot of time, but is perfectly to exchange a message between peers that use variables that is so inertial, like temperature, like humidity, or another kind of variable. There is were no errors due to the loss of the key synchrony, and the implementation of the cyberbox does not affect the security strategy that could be applied by another kind of technology. For example, you can use more power for CryptoBox over the messages that we exchange. That's we test with the Raspberry Pi, and we put some CryptoBox more powerful over the system, and is not alter the information that's double cipher with the method that we propose. That could be very interesting. That's it. Well, that is the idea of the algorithm, and the next step of that's our work is to implement the algorithm in chip. In that case, we implement in like an IP core in FPGA, and try to implement like a ASIC that could be very complicated to block that kind of solution. And the next step is make some evaluation of the solution for try to create some limit of brute force attack that we can use for block the channel. That's, you know, that is always possible that you can block some channel using brute force attack. And we try to resolve another kind of problem for the next step. The next future work is resolve the problem of integrity violation. Yeah, one form of attack that's kind of channel is to try to intercept the message, and another kind of attack is denial of service message. In that case, alter the message and trigger the recover system that could be implemented in the peers. And we try to develop new algorithm that's it's used for message integrity violation. That could be used more cycle of clock in that device, but probably, or it's probably that is not complicated. And we try to test in the robustness of the encryption on system with more research that is if working with a size of key that is limited. The size of key that we use is 2 bytes, is the 2 byte key. But if we can use with more number of bits of key, probably the robustness of encryption is high. In that case, if we use, I think, 64 bits, for example, or more, or 100 to 28 bits, it could be create some strong cipher and with key that is expired for any message that you exchange. And could be a possibility to implement to protect more personal protection in some channels that we use. Well, I don't know if you have some question. I think that's I use the time that you put for me. Yeah, thank you very much.
Thank you, Professor Brown, for your presentation. So maybe if there is some question from the CityView side, so you can pose any question if you have.
Okay, hello, Professor.
Hello.
Hello, Professor Brown.
Yeah.
Okay. From your speaking, actually, I'm so curious about how polymorphic cipher works. So can you explain it for me again?
Yeah, okay. Well, in that case, the polymorphic is because that number, the PS nibble that we use, is used to change the reversible function that we use to apply the key for the cipher message. And for each message that you use, we change the form that we apply the reversible key. For example, if you have 3 reversible key, say for simplification, we can use, for example, the XOR function, and we can use a rotational function, and we can use a display function. And that's this, I don't know with the word for desplazar, the shift function, I think. Shift function, rotation function, and XOR function. For the simplification, we use that 3 function. But when we apply the key, that's the key and the 3 function, we apply in the order 1, 2, and 3. But in the next message, we apply the function 2, 3, and 1. And the next message, we apply the function 3, 1, 2. We can change that function for any message that we send, because the PSIN is changing with the natural of the payload that we use, that we send between the peers. For example, in the first message, we say hello, the temperature is 10 degrees. But we take a part of that message, and that message is used like an index to select the different kind of reversible function. And in the second message, the PSN is used for the index to select the new number that we can use for the index for the reversible function that we can use in the next message. That is a mutation. In any message that we send, we have some mutation that in the exchange message between the people. I don't know if I explain that's kind, but it's very complicated for me though to explain in English. But I hope that if you have some more information, I could write it a more detailed answer.
Okay. I think maybe I got the main idea. So if I have more question, can we contact by email?
Excuse me, repeat me, please.
So I say that if I have more questions, can we contact by email?
By email, yeah, please. My email I will put in the
Chat.
Yeah, in the chat. Let me seconds.
So thank you. While Professor Brown is writing the email on the chat, so I think, Shane, that maybe in honor of the time, we can go to the keynote speaker from CTBU.
Okay. I got it. Thank you.
So,
I say it.
Thank you, Professor Brown, for your presentation. Thank you, Professor Shan, for your question. And we hope that you can communicate by email and exchange more information about the algorithm of Professor Carlos Brown. So in honor of the time, I think that we can go to the CTBU keynote speaker.